Morning, students. Today is my fifth lecture of the subject CE 505 Environment Engineering 2. Topic is the quantity estimation of the stormwater. Last third and fourth lecture, that means today's lectures, we have discussed on the quantity estimation of the sanitary sewage. Now today I will discuss the topic quantity estimation of stormwater. Now what is stormwater? Stormwater is mean the rainwater. So when the rain falls on the surface, obviously the movement of rain occurs in form of surface runoff, and these surface runoff resulting out of the precipitation of the rain contributes to the stormwater, which will pass through the storm drain, or simply it is called nowadays in modern scenario the drain water or draining water. Because in two sense the sewage water means we are strictly saying nowadays the domestic and industrial sewage water, and storm water is called the drain water. Now in these lectures today I will show you how the quantity estimation of the storm water is being done for designing the sewering system, whether it is a stormware, whether it is a combined sewer. So definitely the significance of the quantity of storm water is very much important. Now, as we have told that after the raining, surface runoffs occurs and finally it contributes to the storm water. Now this quantity of storm water definitely when it's reaching to the sewers and drains is very large compared to the sanitary sewage water, which we have discussed in my last two lectures, third and fourth lecture. Now let us see the factors on which the storm water flow are dependent. So we'll discuss the factors which affect the stormwater flow. One by one, there are the 8 factors are there. One by one I am just describing. One is the first one is the area of the catchment. Catchment means the area where the rainfalls occurs. So definitely rain falls in the catchment area. Area of the catchment is an impact on the stormwater calculation. More the area of the catchment, more stormwater will flow. Less the area of the catchment, less stormwater will be flowing. Obviously, the slope and shape of the catchment area will have an impact on the quantity of stormwater, because the water path follows the slope of the ground. So more the slope, flowing also will be more. Then the third point is the porosity of the soil. More the porosity, ground infiltration in the rainwater infiltration in the ground also will be more. So surface runoff will be less, because more amount of water will penetrate into the ground, will infiltrate into the ground. So obviously the less amount of water will flow on the surface. So it all depends on the porosity of the soil also. So less the porosity of soil means the more surface runoff, more stormwater flow. Construction in the flow of water, physically we can see what we can see regularly. Trees are there, standing on the roads. Now fields, gardens, etc. These are the obstruction in the passage of the flow of water. So more the obstruction, less flow of the water. Because in greenery area like fields, gardens, etc., there the soil conditions are there. So definitely water infiltrates into the ground. So less water will flow on the ground. So surface area will be less. Surface runoff will be less. Initial state of catchment area like wetness, how much wetty of the ground is there, that also will have an impact on the flow of stormwater. And very important thing, intensity and duration of the rainfall. One is the intensity, suppose millimeter per hour, how much raining has been occurred per duration of the time, that is the intensity, and how long the raining was done, that duration of the rainfall. That two are very important in the case of the stormwater flow. So obviously more the intensity, more will be surface runoff. More the duration, definitely the stormwater flow will be more. And the climatic condition like summer, winter, temperature, humidity, that will also have an impact on the stormwater flow. Number of size of the ditches, that is the last point which will affect in the present area. That means if there are some ditches, first the ditches has to be filled up by the water, then the water will flow over the ground. So it also depends on the number of ditches existed presently in the site area. Now the measurement stormwater means the rainwater, as I have said, how the rainfall is being measured. The instrument which is being used for measuring the rainfall is called the rain gauge, and that rain gauge may be manual rain gauge, or in modern scenario automatic digital rain gauges are also there. Now what rain gauge actually does, it records the rainfall in a particular time, that means called the particular unit time, so that we can calculate rainfall divided by time, the intensity in terms of millimeter per hour or in terms of centimeter per hour. So what rain gauges give us? Rain gauges give us the rain intensity in terms of millimeter per hour or in terms of centimeter per hour, practically done at site at the rain gauge station. Now methods on slowly I am entering into the mathematical computation part of calculation part, how to estimate the storm water. Now there are two methods we generally follow, that is, one is the rational method and second one is the empirical formula method. In both the above methods, quantity of storm water is considered as a function of intensity of rainfall and the coefficient of runoff. As we know, the intensity of rainfall more means the stormwater flow will be more. Same thing we can see in different way, the duration of the rainfall, the coefficient of runoff C is more means the surface runoff will be more. That is, the stormwater flow will be more. Now the very important factors, the timing factor, that is a time of concentration, which is very important, without of which the no stormwater flow can be found out. And this is very important concept, the time of concentration, that you have to understand. Why it is so important? Because it is the period, that is, it is the interval of the time after which the entire catchment area where rain falls will start contributing to the runoff. That means it is the time, so that the entire catchment area, just at that time, when that time is over, it starts the runoff, and that is called the time of concentration. If we consider the rainfall with duration lesser than the time of concentration, then definitely we will think of that condition, that the situation will not be at that moment where the runoff, where the catchment area started the runoff. So still there is a time to fill the catchment area by the rain. Still the contribution of the catchment area is not started in form of runoff. So in that case, if we consider the first case, if we think about that the rainfall with duration lesser than the time of concentration will not produce maximum discharge, because we have seen that maximum discharge will occur when the catchment area started in contributing the runoff, and that is possible only when the time of concentration reach not less than the value of the time of concentration, because still the catchment area needs to fill up by the rainwater, and then it will start contributing to the runoff. This is one aspect I am thinking. Second, vis-a-vis, just opposite way, if we think that the runoff, if it can be considered, runoff may not be maximum even if the duration of the rain is more than the time of concentration. Earlier we have considered, we have seen the case, if the time of consideration, that is the time of consideration, if it is less than the time of concentration. Now we are saying, let us consider the point where we are thinking that rain is more than the time of concentration. What will happen? Because more the time, rain slowly, what will happen? Slowly will reduce. Rain intensity will reduce with increase of time. So then also the runoff may not be the maximum. So what we can conclude from these two factors, we can conclude that runoff will be maximum we can conclude that the runoff will be maximum when the duration of rainfall is equal to the time of concentration, also called the critical rainfall duration, and that is why it is very important terminology in the stormwater runoff, because the runoff will be maximum in the time of concentration. That means the catchment area started to run off when it is filled by the rainwater. So the time of concentration is equal. Mathematically, let us see how do you compute the time of concentration. It has a two part. One is the inlet time. That means when the rain drops falls on a remote area, and from that area the distance time taken by the distance travel from that remote area to the inlet point of the sewer or drain. That is one part that we can consider the inlet time. And secondly, the second factor of the time, I am emphasizing the path of the drain, I am emphasizing the path of the sewer, the time required to travel the whole distance of the sewer, which is called the time of travel. So in figure I have tried to explain you the sewer length and remote point. That means from remote point to sewer mouth is 1 point, and from the sewer mouth to the ultimate distance of the outfall of the sewer is called the drain path. So this is, again I am telling, the inlet time, how it can be calculated. Some methodology is there to calculate the inlet time. Now I am going to the mathematical portion. The time required for the rain in falling on the most remote point of the tributary area to flow across the ground surface along the natural drains or gutters up to the inlet of the sewer. That means where that storm water started to enter into the sewer. That is why I am calling it up to the inlet point of the sewer is called the inlet time. As I have shown in the figure, again I am showing you the figure that from remote point to the drain inlet point, that is point A, that is one part, and travel time means from A to B, that is second part. So from remote point to A is the inlet time, and A to B is the travel time, that I am going to mention. So the inlet time Ti can be estimated using relationships similar to the following. What following? Now these coefficients will have different values for different catchments. Definitely different values for different catchments. Now T suffix I is in the inlet time equal to 0.885 L to the power 3 divided by H by 0.385. Now what is L? What is H? L is the length of the overland flow in kilometer from critical point to the mouth of the drain, as I have shown in the figure. From critical path to the point A, again I am showing in the figure. Just let me show the figure. From critical point, that is the furthermost point, to the point A, the horizontal travel distance, overland distance is the length of flow distance in kilometer is the L, and the H is the total fall of height, that is the level difference between the critical point, that is the remote point, to the mouth of the drain, that is the mouth of the point A. So length of overland flow in kilometer from critical point to mouth of drain, and H equal to total fall of the level from the critical point to mouth of the drain. So this, if we know, then we can calculate the Ti, that is the initial time. Fundamentally, which is very easy, the time equal to excuse me, time equal to distance by velocity. But here some empirical formula, by applying formula I am using the incident, the inlet time, that is Ti, 0.85 L whole to the power 3 divided by H whole to the power 0.385. Now time of travel, one part, the first factor I think I've been able to explain you the time of concentration. First part is the inlet time. Now the second part I am talking, that is the time of travel. What is the time of travel? Time of travel, that means, again I am showing to that figure before describing the thing. A to B. A to B, I have shown you the sewer, that is the drain in the line. Already in A is the mouth of the sewer. We have reached in the inlet time here, over here, and from A to B the traveling time started. This I am going to say. So if I can say that time of travel, the time required by the water to flow in the drain channel. Here I will apply the principle that time equal to distance by velocity. Distance means here at the distance I am talking, that is nothing but the length of the drain, and velocity means velocity of the drain under the sphere, velocity inside the sphere, velocity of flow throughout the sphere. So time travel tt is nothing but the length of drain divided by the velocity in drain. So this is all about the time of concentration. As we know, the time of concentration is the time where the catchment area started to contribute the runoff flow, and that is the maximum time for the stormwater runoff. Runoff coefficient, then second terminology, I am going to tell you, going to acquaint with you the term runoff coefficient, which is very important, because more the runoff coefficient, more surface, more stormwater runoff flow will be there. So the total precipitation falling on any area as dispersed as percolation, evaporation. Whenever rain falls on the ground, some portion is percolated, that means infiltrated into the ground. Some portion is lost due to evaporation. Some portion is going to the storage ponds, natural ponds reservoirs, and balance portion will surface runoff. That means what we can see? We can see that the total runoff, total rainwater is not flowing as a surface runoff. A portion of the total rain is flowing as a surface runoff. That means since we are talking for a portion of the total rain, that means the fraction is coming. So obviously the runoff coefficient concept is coming as a fraction, which is used as a fraction and which is multiplied with the quantity of total rainfall to determine the quantity of rainwater, which will reach to the soil. So this is the thing. Now the runoff coefficient depends upon the porosity of soil cover, wetness and ground cover. The overall runoff coefficient for the catchment area can be worked out as follows. As we know, the region to region, area to area, there are various surface runoff are there. As we have seen that greeneries area, soil, where there is a soil surface, then the soil percolate under the ground, then the surface area is less. If we talk about the rigid concrete area, then the surface area is more. So in a big region, so there are several subdivided areas where the surface runoffs are different. Let us talk about n numbers areas are there, A1 to An, where the surface runoff coefficient is C1 to Cn. Now, how do you calculate if this area, suppose the area I have divided into n numbers area with n numbers of surface coefficient of runoff, then how I can calculate the overall runoff coefficient of the whole area? The formula is overall runoff coefficient C equal to sigma AC divided by sigma A. That means simply we are using the weighted average for calculating the overall runoff coefficient C. What is sigma AC? Sigma AC is nothing but A1C1 plus A2C2 to A1CN divided by sigma A. So this way we can calculate the runoff coefficient of the whole area, which independently have different areas having different surface runoff, no matter it is, by using the weighted average. Now we have to know, for calculation purpose, then we have to know the runoff coefficient of different area. So I am giving you a idea, a chart, so that you guys have an idea when you will work on the different area for computing the total runoff of that particular area. Let us see in the business area there, where office buildings and theirs are situated. In business area, surface runoff will be taken as a 0.7, 0.9. Apartment areas, that means dwelling units, residential units, quarters, flats, buildings where you stay, dwelling units where we stay basically. There the apartment area is buildings in 0.5 to 0.7 surface runoff. If we talk about single family area, means single family means I mean to say single story or standalone building or standalone flat. So single family areas, they are 0.3 to 0.5 is the coefficient of surface runoff. Very interesting to note that if we talk about the parks, playgrounds, lawns, basically these are the greenery area, soil, made up of soil. So obviously there is a soil, then percolation of the water into the soil will come into the picture. As the percolation of the soil is taking place, So definitely there is a minor overflow, and that's why I can establish that the coefficient of runoff is minimum over here, and that is shown over in the table. It is 0.1 to 0.25. If we talk about the pavement streets like concrete road, rigid pavement roads, there the chances of the water percolation under the ground is very less, maybe negligible. So it is maximum surface runoff, that is 0.8 to 0.9. And same thing, last item, watertight roofs also have the watertight, means the water cannot be percolated, so everything will be surface runoff. Since it is watertight roofs, so it is 0.7 to 0.95, again the high value of the coefficient runoff. So guys, I have given you a guide idea about the area wise what will be the coefficient of runoff, so that you can compute the total area surface runoff, which is basically required, because without the surface runoff you can't compute the quantity of storm swage. Now these are the empirical. Let us discuss about the total quantity of flow in two methods. One I will discuss, that is the rational method. What is rational methods? Now rational methods is where the logic I can establish from the formula, that is called rational method. Q equal to CIA divided by 360. This is not the formula being built from experimental basis, from experimental survey basis. This is basically the logic basis. Suppose A is the area in square meter or hectare or whatever it is. It is a square thing. I intensity is a single dimension. So when I am multiplying millimeter or centimeter I, intensity per hour or per whatever it is, per unit duration, per time duration into area, that means square, ultimately it is give a cubic value, that is the quantity of storm in meter cube or cubic meter, divided by the intensity. We are talking about the duration we are taking, so ultimately we will get the discharge divided by time. How discharge? Because if you multiply the intensity with area, we will get the volume of water of that place, catchment area, and that is nothing but the discharge. Volume of water per unit time is nothing but the discharge. And C means, as we know that all the intensity of the rain will not surface, will not overflow. A portion will overflow. So that's why the concept of C, that is the coefficient of runoff, we are multiplying with the factor. And what for 360 has come? It is the conversion factor has been inbuilt into the system. It is logically established. It can be proved logically how 360 is coming, but that is not our scope of our work. We have to use this formula. But for your knowledge, I am telling you this 360. This conversion factor has been created because we are seeing that here the A, which will be used as a drainage area, that is in hectare, that is 10 to the power 4 square meter, that is in hectares. But ultimately Q, quantity of the discharge, you have to calculate in the cubic meter. Since there is a conversion of the hectares to cubic meter, definitely the conversion factor, the 360 factor has been put for ultimately converted into the cubic meter. Same logic we can say that if we consider the other unit of the same area, same formula, this is the same formula we can write in a different manner, 0.278 into CIA. Why 0.278? Because we are considering the A in square kilometer. Earlier we have considered in A in square hectare, but now I am considering in area in square kilometer. So basic formula CIA is same. Only thing is, earlier I have seen divided by 360, and in this case we are seeing that multiplied by 0.278. So this is the thing, how we can calculate the discharge, that is the meter cube per second, applied the rational formula, that is most logical formula, which can be established or which can be proved by simply expression, by simply multiplication of the intensity and area, taking into consideration of the coefficient of runoff, that is the C. Now there are other formulas also which are called the empirical formula. Empirical formula is based on certain experimental basis it is found. Let us consider the empirical formula. The empirical formula are used for determination of runoff from very large area. Various empirical relationships are developed on the past observation, but here I will highlight only 3 to 4 basic empirical formula which will be used for prediction of stormwater runoff for that particular catchment. Now, three empirical formula here I have highlighted. What is the Buckley-Ziegler formula, that is QP equal to CIA divided by 141.58 square root of S by A. Second one formula is the QP equal to CIA Makaut formula, that is based on USA Makaut formula, that is QP equal to CIA divided by 148.35 square root of S by A. And third formula is the Fuller's formula, that is QTB equal to Cm whole to the power 0.8 divided by 13.23. All these formulas are based on the experimental and facts developed by different experts, and according to their name, the formula has been lodged. Now, in first formula, if I see that first formula and second formula hardly any difference except 141.58 and 148.38, and one is 4 square root and another is 5 square root. That means what is S? S is the slope of the area, and what is C is already discussed, that is the coefficient of runoff. I is intensity, A is the area of the catchment area, that means where drainage area, rather we can say in hectare. And third formula, if we see Q equal to Cm whole to the power 0.8, then M is drainage in square kilometer. So that's why it is indicated as M to avoid any confusion. And first two formula, the drainage area in the unit is hectare. So first two formulas area in hectare, and second last formula area in square kilometer, and that's why it is denoted by the separate letter M. So this is three empirical formulas for discharge. Now I will discuss the empirical formula for rainfall intensities. These relationships between the rainfall intensity and duration are developed based on long experience in the field. Under Indian conditions, intensity of rainfall in design is usually in the range of 12 millimeter. That is our experience or statistical record of our rainfall records, which we have found that in Indian scenario, the design is usually in the range of rainfall intensity in the design is being considered from 12 millimeter per hour to 20 millimeter per hour. In general, the empirical relationship has the following forms. What is that form? The I equal to A by T plus B, or I equal to B by T to the power N. All these things A, B and N are the constants, and these constants are basically calculated from the statistical records, from the graphs, plotting of the graphs I versus B, and from the graph you can calculate the E, B and N. Let us have a knowledge. Let us see the how the intensity fluctuates with the rainfall. You see, more the duration of the rainfall, intensity of rainfall, you see it is decreasing as the duration of rainfall goes on increasing. Obviously 5 years, 10 years, 15 years, 20 years rainfall I have seen, all the rainfall curves are in same pattern. That means the rainfall duration as that means the decreasing pattern of the intensity rainfall. Intensity means millimeter per hour. Rainfall intensity pattern of the intensity of the rainfall pattern is decreasing same way, irrespective it is a 5 years, 10 years, 15 years, 20 years. That I am going to highlight to you. Now, another formula for finding out the empirical formula for finding out the intensity is that is called the British Ministry of Health formula, I equal to 760 divided by T plus 10. That is for the storm duration 5 to 20 minutes. If we increase that, if we talk about the duration 20 to 100 minutes, then this formula under the same British Ministry of Health formula, the expression is going to change, and it is 1020 by T plus 10, where I is the intensity of rainfall in millimeter per hour and T is the duration of storm in minutes. So these are all about the stormwater estimation, my dear students. So basically you have to understand the concept, the basic concept. Second, I am repeating what we have highlighted. First, we have seen on what factors the stormwater calculation on which we are, because the engineers always have to consider the factors in designing the system. There always have to, what are the factors, the design which you are going to do, on what factors that will depend. So first, various factors we have described on which the stormwater flow depend. Then we have seen that how the rainfall is measured, and what are the what is the mechanism of estimation of the stormwater. So two methods we have seen, one is the rational and the empirical, and very important topic without of which the stormwater runoff cannot be found, that is the time of concentration. And why it is so important? Because it is the period which is the time which the entire catchment area will start contributing to the runoff, is called the time of concentration. We have seen, if time of concentration, if time we can consider less than time of concentration, then also the flow will be minimum. And if time we consider more than time of concentration, then we have seen with more time then intensity decreases. So again the surface runoff is less. So time of concentration gives the highest flow value, highest runoff value. So that is the importance lies with the time of concentration. And mathematically, in mathematical computation, we have seen it has the two parts: inlet time and outlet. Inlet time and time of travel. Inlet time is nothing but the time required for traversing the distance from the furthest point to the mouth of the drain, where just it enters. And second part, that is the travel time. Time of travel is nothing but the time of travel in the sewer, that is in the drain, that is the total drain distance divided by the what is time? Time is distance by velocity. Distance means length of the sewer divided by velocity of the sewer. Then you can calculate the travel time. So these two, adding inlet time and travel time, will give the time of concentration, which is very important. Then we have seen the inlet time, how to calculate. So then it is depends on the traveling distance as well as the vertical height fall between the initial point and the final point. So that point we have also seen that inlet time, how it calculate, and time of travel we have already shown, because it is time equal to distance by velocity. And then the factor runoff coefficient of various areas, just have tried to give you an idea which area, what type of runoff coefficient is there, because when surface runoff flows, it covers with various areas. So as an engineer, you must know which area having which surface coefficient of runoff. Now, rational method we have seen how to calculate the quantity of flow at the end of the day, when C is given, I is given, and the area, obviously the area where you are going to find out the estimate, that area is known. Two formulas of the same formula with different units I have described, and then the empirical formula, three formula I have discussed about the empirical formula also, and finally I concluded the empirical formula for rainwater intensities. So this is the thing of the today's lecture. Again, I will in my sixth lecture, that is in the next lecture, I will complete this topic, that quantity estimation of stormwater, solving some numericals, where I will end this chapter, and I will end this topic after having some solution of some numerical problems. So I am just giving you the time to go through these lectures first. Again, we will interact with the live classes. Interaction will be there. Questionnaires will be there. Tutorials, MCQ questions, assignment will be there. Only you can go through the lecture materials. Then only it will be fruitful for us to go ahead. So thank you very much. Have a good day. Bye. Thank you.